my talk is going to be a bit more on the professional side, but I'm going to present a number of ideas that are usable not only for professional arrival stars work, but also advanced analysis of amateur observations. I'm only going to bother you with one formula here, so this is not a place to learn how to use any of these methods. This is more the place to get ideas and maybe resources what to search for if you feel that something that there's a method that you are interested in using. It's supposed to be your impulses to do more of your own research and maybe ask afterwards. So I'm going to talk about searching periodicities and determining periodicities in light curve data of arrival stars. In the cases where it's not that well defined. And yeah, so this is very much going to be based on the stuff that I do for my own studies and what our group does. It's also what I consider involved in doing concerning these master thesis. So yeah, as you all know, the sky is full of periodic phenomena, and certainly the easiest way to find periodicity in astronomical phenomena is to observe a periodic arrival stars. There are loads of them. And I couldn't check the numbers, but I think it's easily the majority of arrival stars have at least some sort of periodicity in them. But when you look at the light curves that are periodic, you quite quickly see that not all of them are very stable. So you have this. On the other hand, you have these light curves, for example, Cepheids or eclipsing binaries that can be extremely stable, so that they can stay for decades or centuries, even totally unaltered. But then again, you have stars like Mira stars, where every single pulse of their variability has a slightly different shape, or semi-regulars, where both the shape of the light curve and the period of the light curve is constantly changing. So there's only a general pattern that's repeating, and then you have variations of that pattern with the same time scale as the periodicity itself. Yeah, so I talk about Mira stars, and even these eclipsing binaries, when you observe them closely enough and for a long enough period, you observe that there is some variation between the forecasted time of the eclipse and the actual realized time, the observed time of the eclipse. So you can plot these graphs of observed versus predicted eclipse time and see changes there. So the more carefully you observe these periodic stars, the more of them, the larger and larger part of them turn out to be not strictly speaking stationarily periodic. So there's complex variation there. And a particular case that what I've been doing are these spotted stars. So we are talking about stars that have strong magnetic activity, as the sun has, but the activity is orders of magnitude larger. So in the case of the sun, we have relatively small sunspots and sunspot groups. Small in the scale of the total size of the star. With these incredibly active stars, which can be fast rotating giant stars, or then young solar-like stars. The spots or spot areas can be of the same order as the star itself. So you can have a spot area that's roughly 1/10 of the visible size of the star, or even up to half of the star. So these are stars which are basically filled with spots. And as with sunspots, these star spots are constantly changing. So here you see for one very famous spotted star, FK Comet, some modern light curves, so you can see that the light curve is constantly changing based on where on the star the spots are. So if you track the light minima of these light curves, you can see that the longitudes of the spots don't stay stable. So on one location you might have a spot at a given epoch transiting your line of sight. But when you go, say, 1 month forward or half a year forward, the spot structure might have been moved to the other side of the star or 90 degrees. So it's not a clear sinusoidal curve. The change of the light curve is quite complex in a way. And even you might have that the spots disappear, or you might have spots evenly around the star. Yep.
Is this particular star, is it a single or quite double star?
This is a single star. This is actually quite interesting star because single, very rapidly rotating star, but it's a giant star.
Oh, yes.
So it's a giant star that rotates with a period of 2.5 days. So it's incredible, and the current theory of how that's possible is that it's actually it used to be in history a close binary system, sort of similar system that the W also measures stars. But as the components evolve, they merge together. So the theory is that this star is a merger of two binary companions. So sometimes the light curve can level down, and with these kind of light curves, you can only barely see that it's periodic, and you can even get instances where it's totally impossible to get any periodicity because there are no spots, or the spots are totally evenly distributed. And also you get period variations on these. So with the sun we know that there's a differential rotation. If the spot is close to the equator and closer to the poles, it exhibits a different rotation period. So with these stars, if we have a spot, or the major part of the spot structure is on different stellar latitudes, we might expect to observe a different photometric period of the light curve. So that is also changing, and it's actually one of the interesting things that you want to model out of these stars. And those previous observations were ground-based photometry, taken with those particular ones were taken with a 10-inch robotic telescope. Then, when you have larger and larger telescopes, or when you fly your telescope in space, you notice that you start to notice two things. First of all, every single star starts to be at least a bit variable, and the variable stars start to be highly non-stationary. So this is Kepler photometry. So a photometry taken by the Kepler Space Telescope of an eclipsing binary. So here you see these grey dots that I've marked with grey are in eclipse observations, and the black observations are out of eclipse observations. And you see there is this wavy pattern, and this is sign that this star not only has eclipses, but at least one of the components has star spots on them. So this is a typical signal of spotted star. So it's more or less a nice wave, but the shape of the wave is constantly evolving, and here you see you start to form another minimum here, and this between these two rotations, one of the minimum takes over. So you can, for example, the simple way to explain this is that there's a spot, there's a decaying spot on one side of the star, and on the other side of the star there's a growing spot. And on one at a certain point of time, one takes over the other. Also, an interesting thing here is that when you have periodicities, you very easily can have multiple periods. So these eclipses are a clear sign of the orbital period of the system. And there are primary eclipses and secondary eclipses. And here it's very clear. You have primary eclipses on the primary light wave minimum, and the secondary eclipses are more closer to the light maximum. But when you go here, actually the situation turns over. So the primary eclipse has been on the light maximum, and the secondary minimum has been on the out of eclipse light minimum. And this is a sign that the rotation period, at least that rotation period that we can check from the spots, is different than the orbital period of the system. And well, basically it tells us that while this is an eclipsing binary system, it's separate enough so that the stars still rotate more or less on their own, and they are not totally tidally locked. Maybe when this system evolves, these two periods merge together. So much. So that's the principal setting. We have loads of complicated periodic signals there in the sky and in our data. So how best to model this? Well, in astronomy, whenever you want to do period analysis, the simple answer is use a power spectrum. So calculate the power spectrum of your data. This is there are people who do this knowingly. They know I want to do exactly this. There are also people who don't think what they're doing. Well, I just learned this method in my undergraduate studies, so I just use this. And sometimes it works, sometimes it doesn't. The idea of this is that, well, it's basically you can calculate it out of Fourier transform of the data. Better way to visualize what it does is that it's one method to fit a number of sine curves to your data. What this method assumes is that the data consists of components that you can model with a combination of sine curves. Sometimes this is a very good assumption, sometimes not so. For example, try to use this for eclipsing binaries with very well-defined eclipses. You won't get any good results. It just won't work nicely. And the other assumption is that you have more stable frequencies or periodicities within your data throughout the data set that you use for the modeling. So this method doesn't allow you to track any, by itself it doesn't allow you to track any changes in the periods. So this can mean either that the data consists of a number of totally stable sine curves that stay unaltered till the end of time, or then you might have the sine curves growing and decaying, but at least as they grow and decay, they do that only with a certain number of well-defined frequencies. So where this works well, we will start with sort of non-violent pulsations. Then it will work well, because these stars, especially if these are very low altitude pulsations, so with astroseismology, with these space telescopes, this is the way, the general way that the analysis is done. These are small pulsations from the star, very low amplitude pulsations, and it's very simple to assume that they are sinusoidal, simple waves. But with also with some higher amplitude pulsating stars, for example, delta Scuti stars behave quite nicely with this kind of methods. So the light curve shape is evolving there, but it's evolving is due to different pulsations of different frequencies, and the pulsations are not too complicated in their shape. So yeah, so this is an example of you using this power spectrum method for real data. So this is data photometry from it's a blue subdwarf star. So it's basically a star that used to be a giant star, but due to evolutionary reasons, it has lost its outer envelope. So in essence, what we are seeing here is only the core of the star as a bare naked core. And this is the whole photometry that they used for this. These guys used for their paper. This is taken by the French Corot space telescope. And this is a section out of the data, somewhere here. So you can see pulsations here, and the red curve is the model that they have fitted to this data. So you see that they are relatively simple pulsations, but the shape of the pulsation is constantly evolving. But as you can see in the next slide, this is the power spectrum. So a bit different power spectra here in the top and lower half of the complete data. So you can see that there are a number of frequency spikes, and these red lines denote all the frequency spikes that they used to model the light curve, and the red curve in the previous slide was built based on those frequencies. So sine curves with those frequencies. So for some stars, this kind of very simple approach works remarkably well, and these frequencies tell you physics about the star. So you can infer some internal structure of the star. Here in the bottom you see confirmation that this method works. So this is the power spectrum of the full data. Then they took out the number of frequencies, made modeling, subtracted that model from the data, and here is the power spectrum of the subtracted data. So that should be noise, and then this spectrum should be only noise. And yeah, I agree that it's pretty much only noise. So it works well. Bad for my hands. So in all cases, this doesn't work at all. So there are cases, for example, in our study with these spotted stars, we don't want to make the assumption that the system, the periodicity is described by sinusoids. It might work well, but we don't want to make that assumption. And also we are interested in the variability of the periods. What you can do then is one way is to split the data up into slots, and do the periodic modeling for each of those slots. You can have just pieces of the data following each other, or then you might also do a sliding window. So you take a slot of data, analyze it, move the slot one day forward, analyze it, and move. So do that with 1 day intervals. And it all depends on what you really want to do with your data. Of course, you have to decide what the length of the data set you want to use for your analysis. This is a case where you have to do testing, and you really need to play with the data to get to know it. So you need to decide what's the best length for this data set to really get proper result. Too short, you will get too few data, and your analysis won't make any scientific sense. Too large, and you have too much variation already within one set, and then you, in a sense, lose exactly the variability that you want to track. So the method that we are using, here is the name, and we published it a few years ago in its latest form. Basically, we model the data sets with a low order Fourier series. So with this kind of model curve. So it's with some mean value, and then sine and cosine curves with independent amplitudes. And so basically you get free wave-like fit for the data. And also here you see frequency, so the inverse of period as a free parameter. So we also model the periodicity. And out of this modeling, you very easily get the light curve, the mean brightness, mean magnitude, the amplitude of the light curve, and the period of that particular data set. And you can also compute out of the results either the minimum times or the maximum times of the light curve, and those might be interesting depending on depending on the science or analysis you want to do with your data. For example, with these spotted stars, I think that those are one of the most interesting things. And here's another parameter that you have to set. You just have to decide the order of the modeling. You have to know your data a bit to know what's the best. In general, this doesn't have to be too high. If you look at the data, it's quite simple in its form. So there are no very sharp variations. It's quite smooth. So this can be usually setting this to. So only taking the mean value and first and second order sine and cosine terms will work. Sometimes you want to go to 3. If you want to use this kind of method for something like cephase, then you would want to go to something like order 5, but in no case above that. So the ideal of this is to have a simple, well-behaving modeling approach.
Sorry, what is K?
So here I have 2 Ks. So the small k number is just the number of that particular model order.
Yes.
So 0 is for the mean level.
Yes.
1 is for simple sinusoidal curve with the period of the actual star, and 2 is for the first overtone. So it has twice the frequency, so half the period. And when you have the first and second order, that means that you can have some shape variations within the curve. Then this large K is the limit of to which order you want to go. So, but yeah, this is all mathematics. So it's best visualized if you draw curves and then decide, okay, this seems to be nice for my work, so I'll settle with this. So this is an example of what you will want to do. So this is from our recent paper with another famous spotted star, LQ Higher. This is raw photometry. So this is ground-based photometry taken with a 60 centimeter robotic telescope. And we have quite a decent amount of data. So at this point there's also a couple of more years, so it's more than 25 years at this moment. This is the Johnson V-band photometry for the star itself, and this is check photometry for an non-variable check star. And then for this actual dataset, we have run this sliding modeling, and here you can see the mean, magnitude, and it's pretty much as it should. It follows this, but it's now you can see the mean level much clearer, so you can see all these short timescale variations as well. And you can also see very clearly the amplitude variations, and there are clear variations with this star, although it's not immediately clear what's happening there. Are there any cyclic variations there? Is there any connection between this and this? And then finally the period value of the star. And you can see that well there's some scatter with the observations and some values with quite high errors. But there is some variation from year to year. So there might in fact be some not only random variations from one segment to another within the star, but also from year to year, so systematic changes. So yeah, this is something that using this kind of sorted method allows you to do. Another similar method is not to cut the data into slots, but use all of your data on one go. Then, of course, as the light curve evolves, you want to introduce a bit more complexity to your model. So the idea is that if we come back here with this model, you're using all of your data there, but each of these model parameters, n, bk, ck, and also the frequency, has time dependence. And as a result, you can get this kind of smoothly variable light curve fits. So this is one single fit for quite a stretch of data. So this is data during is it something like, well, it's more than half a year. It's one full observing season, and here you can already see the fit to the data, and here are residual values of the model versus observed values. So it's roughly even and pure noise. So it's the fit works well as well. And yeah, you see all these strange shape changes in the light curve. So if you really look at these kind of fits, you can also make quite involved guesses on what's really happening on this star. So these two methods are pretty much two different ways to do the same thing, and we've done studies where we use the two methods for extracting the same data. And here you can see in these phase diagrams we have plotted, we have extracted the minimum times of the light curves from those two different model fit types, and then calculated calculated the rotational phases when each one is lasted. So which longitude or rotational phase the light curve minimum happen. And okay, here there are also some additional spectrum information, but that's not beside the point. So you can see that the phases that we extract out of those two methods agree quite well indeed. So both of the methods have certain advantages and certain drawbacks with respect to each other, but all in all they tell us the same thing, which tells us also that they tell us the truth. Yeah, as you can see here, the smooth carrier fit method that takes all of your data in has a smoother solution, so it can, for example, here you have a noisy problematic portion of the data where one of the minima has decayed away. So this carrier fit method interpolates nicely through it, while the other method, the slotting method, doesn't really do well on that part. On the other hand, we can't really do pretty well with the error estimates for these phases, or in fact any of the parameters with that smooth fitting. So in order to get that, for example, in order to get all of this uncertainty that happens here when there are two spots that appear to merge, then we have to resort to the advantages of the slotting approach. There are problems, of course, always. And one of the problems is that when you are using only a with a limited length to search for a period. Do we have problems with the accuracy that you can get? So this affects especially the case when you only take something like a month of data and model it, and then the second month and model it. But also it affects a bit the other approach where you do smoothly changing it, because then in effect every part of the data is affected only, well, to a large part by the data close to it in time. So if you want to get the periods out and do analysis with the periods and the period changes, you have to notice that also your analysis method creates period variations. And these can be quite significant. There are many stars, many data sets that this kind of spurious non-real variations are far larger than the variations due to the star itself. And in those cases we can't say anything. Well, we can say that, okay, this star doesn't have too large period variations, but we can't say anything else. So this is an example. These are model results, period estimations from a data set that was created to resemble real photometry with period of 7.8 days and realistic noise and realistic observation times. But this is a stable sine curve with a constant period of 7.8 days. And see what's happened here. So you have periods between 7.7 and 7.9 days. So with this kind of sampling and this kind of data errors, you already have quite large errors with the period, and not only the errors, but not only these errors, but systematic errors. So this seems that I see some real fluctuation. This is very interesting. This is a very fascinating star. But no, we know that this data shouldn't have any of that. So you might have quite serious problems with the analysis if you don't acknowledge this. And I did some tests with this. So with this very simple test data with different layers of noise. So this is 5% noise, 10% noise, and 20% noise. So this is this resembles light curve. We close to the border where we can still observe that it's nicely periodic. And then I took different lengths of data. So here I only included 2 period cycles. So one period and another period in the modeling. Here I included 20. And also you can see the number of data points within all of these. So now it's inversely here. So basically it means that these highest values are 10 data points and these lowest values are 100 data points within the data. And you see that it all affects. The more noisy your data is. So okay, I should also explain the vertical axis. So this means the relative scale of the period variations. So it means the scale of this variation with respect to the period value. So the ratio of this variation with the actual period. So you see that if you have short periods, so that you can take say a month of data with only a 1 or 2 day period, you can take 20 or 30 periods even. You get lots of data, and if the light curve amplitude is large, you have small errors. So then you can get smaller than 1% variation with this kind of slotted analysis. But if your errors are larger, or if you are forced to use less data, and the period of the light curve is long, so you can't use too many periods, then you end up somewhere here. So in the worst case, you see more than 10% variation in the periods. That's huge. You expect that something real can be there. But if the real variation is around this level, you see that with these cases that you can use only a few period cycles, you can't really do cycles with the period variations at all. So this is bad news for anything that we want to do with the periods. But it's something that you have to know. You have to know where the methods can bring you, and when they aren't good anymore. If you know a bit more about your targets, you can start to include a bit more physics into your modeling. This is something that has a bit more professional stuff. You have to be quite involved amateur to be able to write yourself a code that involves physics of the actual star system, unless you are collaborating with scientists who have already written the code, and you can just use their code. But you can do stuff like that. So again, with these spotted stars, there are people who have done spot modeling. So okay, we know that this variation consists of spots on a star, and the spots can be on various sizes, on various longitudes and latitudes on the star. They can have different periods. Here you see frequencies modeled for spot frequencies modeled for one star, and they can live, so they can grow and decay. So here you see growth and decay curves of a number of star spots used in the modeling of one particular star. And yeah, pretty much what you want to get is like this. So this is the model you are fitting. So circular spots on a star, and this is the fit that these guys got for this data. They used this data to get that modeling. Although I must say that this is only a bit more than 2 periods, so based on a few slides back, at least the period value here isn't going to be too exact. So there are problems with this kind of work, and especially here. So notice, whenever you are including physics in a modeling, the results are only going to be as good as your physics. So if the physical model is wrong, it's very likely that your results will also be wrong. So with simple non-physical models, you can do better blind research. So it's also better suited for amateur work. Also, you can very easily create too complex models. So, for example, this spot modeling is an excellent example of model that very quickly becomes too complex. So you can quite easily get the rotational phases of the spot, the spot longitudes, just based on the light curve minima that you observe, but the periods of the spots, as you see on my slides, or on the period accuracy, they have problems. Then how on earth latitudes, how close to the equator or the pole of the star they are. If you have a multiple color photometry, so blue, green, red, so for example BD and or I-band photometry, you can have some data out of that. But even in that case, it's very, very difficult, and I would say highly dubious in many cases. And also you have to do quite some assumptions. So here, typically people assume circular spots. Well, we can observe the sun. Are the sunspots groups circular? No. And we have also spectroscopic information of spots on other stars. And we know that the spot structure that we can map out of a number of stars. Sometimes they are quite circular, blobby. On other times you have connected spot regions and very complex shapes. So all this kind of work involves quite a lot of assumptions that you have to make. And especially if you don't know where the assumptions can go wrong, you can create bad and misleading results. Of course, there are always further ideas. So this is a test idea for a number of stars. Later on, with methods to model the mean light curve level. This is a spotted star yet again. So with these cycles, you could say that, oh, this is an activity cycle. If it's an activity cycle similar to the activity spot cycle on the sun, we want to get the period out of this because it gives us important science, important physics of the stars. But how to get the periods out of it if the shape is so variable? So this was an attempt to play around with ideas that allow great variability of the shape of the variation from one cycle to another. So to conclude, in order to do the modeling, you need to know how your data behaves. If you get total new data out of a star that you've never observed, and might even be very poorly observed throughout the world, it might be difficult, but that basically means that when you get data, play around with it. The first analysis that you do to it might not be perfect, and it doesn't have to be perfect. But what you have to do is do the analysis many times over and over again and improve on what you have to learn, what you have learned on it. Basically, there are complicated ways to model the data, but there are also simple ways to model the data. And even with these simple ways, there are more different ways. So choose whatever suits that particular data and your own interest the best. And also, this is science. In science, you're basically allowed to do anything as long as you tell exactly what you did. So that if it's wrong, people will know how it is wrong. But even if you're doing the right thing, if you don't know what's actually happening, it's not exactly, at least good science. Of course, for us it's hobby, but even there, if it's an advanced hobby for you, you might be interested to actually know how your analysis is working. So, yeah, so just to leave it off with a nice picture. So I hope this gave people a number of ideas. If you are interested, you can ask me now or later, and it's always helpful to read literature. So, for example, read textbooks of textbooks of signal processing or statistics or period analysis. Also, it's very interesting to read published refereed articles of this kind of variable star research. Although if you are working outside the university, it might be difficult to get access to many of this data, many of these publications. But in that case, you can always contact, you can always make friends with some researcher who is interested in the same area and who can provide you with some literature and also help you to understand if the mathematics of it is not exactly your own business. So, okay, I hope I didn't go too much all the time, but thank you.
Thank you.
For listening.
Sorry that I did just late, arrived too late to hear the whole story, but about this modeling of these stars with the sports we have in Finland, quite a long tradition, especially people involved, all like the Ilkka Tuominen's group and those who have PhD in Ilkka's group like Heidi.
Actually, I'm a continuation of this work myself.
And
at this moment, we aren't doing this spot modeling. We are doing what I showed earlier here. So we are doing modeling with this kind of mathematics.
Oh, okay.
So just Fourier series and the results that we get. But it's
for example, if you know the history of this, and has been very successful project in Finland. This like when the knot was the new, and they were wondering what to do with the right time.
Yeah.
And so the Finnish group in all Ilkka Tuominen's group, they built this Sofin, which has just retired, and with the Sofin they did almost 20 years to observe during the right time, and they had high signal and noise resolution.
I was actually present there when Sofin was used the last time.
Where is it now? Is it still?
It's still there, and 2 weeks ago I heard some discussions between our group and Klaus Strassmayer, who was working in So we have planned to, because it's retired from the knot, we have a plan to transfer it to the regular solar telescope on Tenerife to function as the nighttime instrument there. But that means that it first has to be transferred to Potsdam to be rebuilt a bit.
Okay.
And the latest that I heard that they don't yet have everything in place at Potsdam so that it could be transferred. So
does it include also Ilya?
It includes Ilya, so Ilya will be working a lot with this. so it will be I would say something like 2 or 3 years before we can use it with the regular telescope.
So you are now using mostly Sofin at the knot.
So we use
Sofin.
Yes.
What is this high resolution?
Yes. So that's what we are using now.
Yes. But can you do exactly the same with PS and the square method?
Not yet.
Not yet. It's coming.
So this is a bit besides this point, but it has to deal with these active stars. So I can have this slide here. So we do also spectroscopic work, and these colored bars are based on spectroscopic results. So we are compiling these results. So we used to use Sofin a lot, and now we are transferring to the TS spectroscope. Well, TS has 2 drawbacks. It's supposed to have a polarimetric unit already. It's not yet delivered, and I don't think anyone knows yet when it's going to be operational.
Who are building this Swedish collected
I think it's them, yeah.
Yeah. Like they also did that same with the harps at the
Yes.
end.
Yeah.
Added this special parameter facilities.
So we have been applying time for PS to use this as to this point non-existent spectral polarimeter. Just when it arrives there, we are already using it. And the other drawback with PS is that we can't go as high spectral resolution with this. It's not going to provide in that sense as good results. That sort of thing. But if everything goes well and if the funding of the node is successfully also in the future, we will in fact have observations both from them and from the Tenerife solar telescope.
Which size of telescope in Isana it was?
Sorry?
Which Isana telescope it will be located, this Sophie?
So it's the Gregor solar telescope, which is, I think it's 1 meter or 1.5 meters.
It was a solar telescope which we even use it at the night.
Yeah. So it's a reflector telescope.
Yeah, probably it's less than 1 meter because I guess this La Palma 1 meter is the largest.
Well, it's. I think the Gregor is a bit larger, but they are different. So the Swedish solar tower from La Palma it's a lens telescope. So it's the largest lens there.
Yeah.
At least operational.
Yeah.
So if you want to go above that, you have to use euros also for solar physics. So with the research we are doing, it's very much compiling photometric and spectroscopy. So it's all about using as much data as you can from as many different approaches that you can.
Yeah, your physics is showing the conclusion is that the spots are in a particular place as the star is rotating.
Yeah.
Now, these are very large spots. Now, the magnetic fields that are involved, do you think they would actually distort the shape of the star?
Well, no, that doesn't happen because still the gravity is the major force shaping the star. So the gravity creates a much larger force than the magnetic field. And when the star is rotating fast, then you have Coriolis effect.
Yeah.
So that's also a major shaping factor of the star. What is on the same order of magnitude with the magnetic forces are pressure, thermal pressure of the gas. So that means, well, that's what you see in the sunspots as well. So you have magnetic force battling against the pressure of the gas, and that's a major cause of what in fact creates these dark sunspots and star spots. And in fact there you see a bit shape distortion. In these, at least in sunspots, you can see a bit lower in the solar atmosphere because the magnetic forces allow the gas to have lower pressure. So that you can say that the magnetic fields locally make a hole in the or slight depression in the surface. But it's only a local feature, and also it's only if you interpret it like that.
What is your conclusion of the structure of the star with large spots?
Well, basically, if you need the internal structure, that's pretty much the same as a similar star without magnetic fields. So that you can get out of pretty standard stellar evolutionary models for these For stars which have strong evolving solar-like magnetic fields, that means that the star has to be really solar-like. So it has to have convection in an outer shell. It might be a main sequence star, as a sun, or it might be a giant star. And also it might be like the sun or the giant star, so that there isn't any convection in the core. But it can also be, although with different physics, these very cool small dwarf stars, M dwarfs, that are fully convective. So they are internally very different from the sun, but they still generate magnetic fields and have these spots and magnetic activity. Okay, then the spot structure of the magnetic fields, that can be very different from the sun. So and that's on the cutting edge of this research. What is the actual magnetic field structure on the stars with solar-like activity, and on the stars with much higher activity, and on the stars with different internal structure? So a simple answer is the structure can be very complicated or very simple, and it's always interesting, and pretty much anything goes.